The second speaker in the morning is Paolo Stellari from Milan, and he will continue explaining stability conditions and things.
Okay, so thank you very much for the invitation. It's a really great pleasure to be here. So as Emmanuel was mentioning before, we are left to prove this inequality, this Q2 he was mentioning before. So let me just remind you the setting. And just change it slightly the notation, just to remind the dependency of some of the objects I defined before. So X for the moment will be a smooth projective threefold, of course defined over C, and we pick H an ample class. So as Emanuele did, we pick alpha a positive integer and beta a positive real number and beta any real number. So we define so we define omega to be square root of 3 alpha H and B to be beta H. Okay. So we let me just remind you that we have seen how to define this twisted Chern character. And Emanuele recalled us that, I mean, using this, you can define this category. He called, I guess, A2, which, I mean, just to remind you that, I mean, there is a dependence on this guy here. I will denote like this, maybe. Okay? And this is cooked up using the usual twisted slope stability. Okay, then we have seen that on this category here, we can define a function which it has in a very explicit form. It was called mu2 before. Again, I just use this notation to remind you that there is a dependence on alpha and beta. As defined like this, so it's plus infinity if h squared times ch1 beta of blah is equal to 0, and otherwise it's h ch2 beta of blah minus 1/2 alpha square h cube ch0 beta of blah divided by h squared ch1 beta of blah. Okay?
Omega and you use H.
Yeah, and just if you want, this is a sort of in his notation is a sort of rescaling, something like this, of new omega b. Okay, it's a renormalization. Okay. Okay, so the conjecture we have to prove, which is is contained in this form in this paper by Macri et Toda, then reformulated by the three of us, says the following: if E is mu alpha beta semi-stable, of beta of x, then the inequality, so it was Q2 of E, which you can write in a very explicit form. So here you have this alpha square, and you have this sort of discriminant, and here you have a plus, so it's h to beta of E squared minus 6 h2 ch1 beta of E dot ch3 beta of E. Okay? And okay, so we have this guy here. He should play important role. Okay. Now, so what's
And what is delta?
oh, delta is what was called, I guess, Q1 before. Sorry, you know where talk. And as Emanuele mentioned before, this guy is always positive. Okay, so as Emanuele mentioned before, we want to prove this conjecture for X and abelian threefold. Okay, let me make a couple of remarks.
The conjecture is for all threefolds or what?
It's for threefolds, yes.
For all?
Yeah. Okay, you can say something in one of the two cases about Calabi-Yau type you mentioned before, but let's stick to this abelian threefold case. Anyway, so the first one is that, as Emanuele was mentioning, there was the conjecture was proven by Maciocia and Pieratne when X has Picard number. Okay. So unfortunately, this is not I mean, so the conjecture is true if you want, due to Maciocia and Pieratne when X is an abelian threefold. Abelian threefold, yeah, in the same set. Abelian threefold. Sorry. Sure. You're right. Okay. Unfortunately, this is a bit too restrictive to treat the Calabi-Yau case because the examples Emanuele discussed before, to treat the examples Emanuele discussed before, you need abelian threefolds with a higher Picard number. Okay. For Calabi-Yau threefolds, of course, let me say of quotient type. So those discussed by Emanuele in the previous lecture. And there is a case where the conjecture is known to be true. So, if X is any threefold and E is mu alpha beta semi-stable with well, Q1 now equal to 0, then Q2 of E is greater than or equal to 0. Okay? So that means that we will always consider the case that is bigger than 0. Okay? Oh, this is okay. So essentially, this is you reduce to the Schiff case, and then this is a result of Simpson. Essentially, this is I mean, it was checked by, if you want. I mean, we really checked this, but it was checked by Bayer, McCree, and Toda. And the guy here has two cohomologies. Okay, so it means that you can check. You can control further the two cohomologies. And okay, each one is either 0 as a vector bundle, and then you apply Simpson result, and you show that the inequality is true, or is 0, and then you can control H0. then it's a torsion-free sheaf. The double dual is a vector bundle, and then you do the same argument. So it's a direct check. Okay. So let me leave this for a second, and let's go to the to the interesting part. This is just a check and the reduction to sheaves, essentially. Okay, let me keep this inequality for a second. Okay. So let's see how we go on with the proof. So actually, the part has a, the proof has a part which is completely general, so it works for any threefold. So let me first sketch this part. Okay. Okay, how do we proceed? So let's assume that E is a new alpha beta, let's say, stable, and such that the inequality is not satisfied. Okay. Okay, so here we are picking a random beta. So actually there is an ideal beta we want to reduce to. Let me make this precise. So let me define beta bar depending on E in the following way. So this is going to be H CH2 of E divided by H square CH1 of E. And then here you have H square CH1 of E minus square root of Q1 of E. So divided by H3 CH0 of E. So in this case, if CH0 of E is equal to 0, and here otherwise. So that's the guy we want to reduce to. Why? Okay, so let's have a careful look to this special case. Yeah, indeed, actually. So it's a bit hidden in the whole thing, but essentially you should, you should look at this function nu alpha beta equal to 0. That's it's a sort of it's a conic, and then it's one of the solutions intersection with that. Yeah, but it's not really relevant for the purpose of this talk. So the properties are essentially, I want to stress are the following two. So if you look at H CH2 beta bar of E now, this guy is trivial. And if you look at H CH1 beta bar of E, this guy is positive. Okay, unless Q1 of E is equal to 0, which we already excluded. Okay, so that means that if you look at the inequality upstairs, this is positive. This is trivial. This is positive, so that means that so if we want Q2 of E to be negative, we need CH3 beta bar to be positive. Okay. So that means that if you assume that E does not satisfy the inequality, and for some reason you can reduce to the case beta equal to beta bar, then essentially you get for free that this inequality on CH3. Okay?
Can I ask a general question? Is there some easy way of saying like where this Q2 comes from? How did people think of that?
Yeah, I mean, it's as Emanuele was mentioning before, it's a sort of modification of a Bogomolov inequality to take care of CH3, okay? And if you want to think at the presentation Emanuele gave before, so essentially the issues that you want to provide are examples of stability conditions.
Right.
So the big property is to showing that, I mean, the image of A minus 0 is contained in the upper half plane plus the negative semi-line, right? Okay. And now the key point to show this is that you need a bound on CH3, okay? So this one is a sort of rewriting of the bounding on the bound of CH3. You need to impose that the Z function is as image contained in this upper plane.
But I mean, is this formula unique or whatever more kind of?
No, it's not unique. I mean, of course, as Emanuele was mentioning, you can vary, for example, the coefficient in front of this one. But the idea is that this inequality, besides providing the examples of stability conditions, also gives for free this support property that Emanuele was mentioning before. Okay. And okay, then you can deduce also other properties, geometric properties, which later. But that's essentially the reason. Okay. Okay. So let me go on. So the issues that now the key point is that if we can reach beta bar by some kind of argument, then we get for free this bound on CH3. Okay. So let's see how we can move beta to beta bar. Okay. Pardon me? Yeah, indeed. Use it. Yeah, exactly. We get a contradiction using this one, in the sense that, as Emanuele was mentioning, we sort of imitate the usual proof of Bogomolov, and that means that we'll use this to give bounds on the Euler characteristic on some pullbacks of the object. I'll try to explain this rather clearly, hopefully. Okay, so let's see how we reduce. So how we can make the first reduction to beta bar. So we are in this situation. So here we have alpha. You get beta, the beta axis. Somewhere here you have PE. And you start with an object E, which is nu alpha beta stable, not satisfying the inequality. So such that Q2 is smaller than 0. Okay, somewhere in this alpha beta upper half plane. Okay, good. So how do you do now? So consider. So we consider now the semicircle C alpha beta with center. It can be rather explicit. So beta plus nu alpha beta of phi. So there is a dependence on E, of course, and 0, and radius square root of alpha square plus nu alpha beta of E. Okay, and okay, so now that means you get something like this. This is your C alpha beta. Which are the properties of this circle? We want to stress now. Okay, so essentially you want to move along this semicircle. So but you want to move in a safe way. So here the object was nu alpha beta stable. You want to move along this semicircle in such a way that the object remains stable, okay, and in such a way that the inequality remains unsatisfied moving along this circle, okay. So indeed these are the properties. So the first one is E remains nu alpha prime beta prime stable for beta prime, alpha prime in this semicircle. And this, of course, I mean, to show this, you have essentially to show that, I mean, this circle doesn't meet any wall for the T stability defined by Manuel before. And this is rather explicit. So point 2. Okay, now this is clear from the picture. Essentially, is this, again, besides some degenerate case, again, the semicircles. Continuous in its. I don't remember. I don't think so, actually. But anyway. So P is contained in its interior. That's good. And the third thing is that you have that, okay, so if Q2, if the inequality is not satisfied, then it is not satisfied. At any okay, what does this mean? It means that essentially we can move along this semicircle, as I was mentioning before. It's well, was this a Q2 of E? Now there is a dependence on alpha beta, which I'm not mentioning in the notation. So that means if it's not verified for alpha beta, it's not verified for any beta prime and alpha prime beta. So you want, I mean, you would like this to be true. So if you have that this is smaller than 0, then it stays smaller than 0 all around the circle. Okay. Okay. Okay, so that means that you can move along the semicircle and you get to this point here, and now you get beta bar, alpha bar now. Okay, so that means that we can assume beta equal to beta bar moving along the circle. Okay, so we are here. And now the second move you want to do is just start decreasing. So you move in this direction. So you want to start decreasing alpha. Okay, second step. Okay, now you have two possibilities. Okay, so the first one, which is the one we want, I mean, at the end will be the case. So here E remains nu alpha beta bar stable all the way down. Okay, so it does not get stabilized. So that means that there is an open neighborhood of P where E remains for beta prime, alpha prime. Okay, so indeed you have to check something here. Not, I mean, essentially you have to verify that P is not the endpoint of any wall. Okay. So if you are in this case, so you get an open neighborhood U where the object here remains nu alpha prime beta prime stable everywhere there, and we already know that CH3 of beta bar of E is positive. Okay, because of this reduction to beta bar. Okay, so of course the second possibility is that there exists alpha 0 smaller than alpha bar, such that E is nu alpha 0 beta bar properly semi-stable. Okay, now, of course, I mean, the conjecture is not verified, cannot be verified. Okay, so we had this let me write like this. Okay. So again, you're somewhere here. So you move down here, and E is properly semi-stable, but the conjecture again is not verified. So the inequality is not verified. Good. So now what do you do? Okay, and now what you look at this Q1 of each of these guys and Q1 of E. Questions? So the point is that now here you have a strict inequality, and we already know that this guy here is positive. Okay? So that means that essentially, and these guys here are integers. So that means that you can do induction on Q1. Yeah, but I mean, if you look at, I mean, Q1 was, there was a, the beta doesn't matter. Okay, so the issue is that here you have what was the sort of, let me write in without alpha and beta. So it was alpha squared C1 of blah, that is no problem, okay, minus 2. And then here there is a CH0 and CH2, so it's an integer, okay? Okay, so it's an integer. Okay, so we can, that means that you can do induction on essentially on Q1, and it is a sort of elementary knowing implies that giving you the contradiction. Okay? So you're done. So that means, so in conclusion, if E is alpha beta, nu alpha beta stable, and Q2 of E is negative, then there exists U, an open neighborhood of this point PE, where E remains stable, and CH3 of beta bar of E is positive. Okay? So that's the conclusion. Now you want to use this, and for this you need some kind of geometric argument, and then you need to move to the case of abelian threefolds. Okay, and HMA. Okay, so you essentially want to get rid of beta bar again. So you want to move beta bar to 0. Okay? So how do you do this? So essentially you have two cases. So let's assume for a second that beta bar is actually a rational number. So the irrational case would be very similar actually. Okay, so we do the following. So you take take a positive integer such that this guy is an integer again, and then you consider a multiplication map and then you take now an upper star of it. Okay. Again, which are the properties now? Okay, so first of all, if you want to compute beta bar of this new guy, okay, so you do the computation with the explicit formula I gave at the beginning. So this is n square beta bar of E, and so this is actually an integer. Okay? And then the crucial point is that now n upper star of E still violates. Okay, this is not difficult, and the key point is that to remark is that is again stable. Now to this n upper star of omega. Okay, that means that to taking n upper star of e instead of e, you can assume that beta bar of e is an integer. Okay. And of course, now you tensor, and you can further assume that it's 0. So this is essentially, that's a crucial point, that the map is a tal, is a tal map, and essentially and so stability is new stability, this low stability, this tilt stability is preserved under étal maps. Okay. So if you want, so if you have an object that is destabilized, then this has to be the pullback of another object, and so that means that the object downstairs has to destabilize E again. Okay. So this essentially, let me remind, this is we use this also for, if you want, to prove some stronger result about for Calabi-Yau threefolds of type A, the first example mentioned by Emanuele. So when you had type quotient. Okay, so that means so by tensoring by OX minus beta bar of E H, by tensoring, of course, we can assume further the beta bar is equal to 0. Okay, so you can cancel out beta bar. So that means that so in this situation, we don't have any twist again here, and this guy here is positive. Okay. Okay, so what's the situation now? So now if you look, now you take M, again a multiplication map, and you look at chi of M plus star of E. Okay, this is a n to the power 6 CH3 of E. We know that this is positive, so this is greater than n to the power 6. Okay? So what's the trick now? So now you want a bound from above, controlled by a different power of.
What is the MC?
It's a M6, sorry. 6.
So how do you get this? Do you assume that it is greater than 1?
It's greater or equal than 1. Oh, so it's an integer. So it's a chi of E, actually. Yeah. Okay. Good. Okay. Okay, so now you want a bound from above. Okay, so now you get this bound. So first of all, you say the following thing. Okay, we already know that okay. So you observe the following thing. So it is a shift by 1. Okay, so this is co beta equal to 0. So let me write like this. So it's not co x, but it's, again, these are two-term complexes, but with beta equal to 0. Okay? Thus, for positive integers, we have what? Okay, so you compute the dimension of the ons minus k minus 1 of Ox m up star e. Okay, this is okay, so this is 0 because there are negative ohms in an abelian category. Okay. And so that means you can do the same computation. So if you want to compute k plus 2 now, minus our duality. This is just minus k. And again, this is 0. Okay, so that means that if you look at, if you go back to this guy here, so essentially you get a bound of the following type. So if you look at, so we already know that this is greater or equal than n to the power 6, and this is smaller or equal than ohm, and the only other place which can survive is ohm 2. Okay. Okay, so now you want to bound these two guys here, okay? So and ohm 2 is going to be similar, very similar, by subduality essentially. So you do this, so you take, so we have to use stability at some point, so that's the point where we use it. So you get the triangle, so consider for divergent in the linear system of H. Okay? Okay, so now let's observe the following thing. So okay, so first of all, the line bundle OX H, so was implicit what Emanuele said before, is mu alpha beta stable in co beta x for beta small. And you have also that alpha beta of OXH goes to 1/2 for alpha beta going to 0. Okay, and we observed, I mean, we observed that there is a region where there is a region where the guy remains stable, and now if you compute nu alpha beta of E, this guy goes to 0. Okay, so now you want to compute, so what did you deduce from this? So now you want to compute you want to show that okay, 0. So you see that this is just 0, right? Because of this this condition here. Okay. What does this mean? It means that essentially, if you want to bound Hom OX M upper star of phi, then you just need to estimate this guy here. Okay. So the dimension of this Hom space is smaller or equal than Hom OX M upper star of E tensor OD. Okay. And now you are done because you know that E is an object in this category. So that means that so it has two cohomologies. And then you get a triangle. So H minus 1 of E shifted by 1. So pull it back. Okay, and tensor by OD. That means that so it means that if you want to estimate this dimension, then it's enough to compute H0. Okay. And now this guy here goes as OM to the power 4. So ground. And the same for this guy here. And 4. Of course, you have to use a little bit. So yes, essentially by self duality. Okay, so in conclusion, what we get? We had this guy greater or equal than m to the power 6, but this guy going as something which goes with the power 4. So it means that we get a contradiction. Okay. Hmm?
Is there an n to 6 plus?
Pardon me?
In your inequalities, there shouldn't be an n to the 6 plus also.
No, I don't understand. So this was the quantity.
No, the right hand side.
So yeah, goals are something, I mean, the highest power you can get is M4. Okay? So it's essentially this estimate I did here, right? Is a surface, yes. This is a surface now. Okay? So essentially you are done with the case of on 0. And then of course so I'm cheating a bit because here you should in principle we should give a similar estimate for OM2, right? So I think, yeah. So I've just shown that this quantity here goes as a n to the power 4, but actually the same similar argument. Yeah, well, maybe if last effect and now. So you have to, I mean, it's actually stable. So essentially you use the same trick, use stability, but with a different line bundle, okay? Okay, so during the last 5 minutes, maybe I can just tell you how it works for the irrational case, which is very similar. So the last case we have to consider is this one. And for this, we essentially approximate beta bar. Beta n. Oh, sorry. Okay, now what you do now? So you compute. So essentially, beta bar is a sort of minimum for these guys. Indeed, if you compute this third channel character, I mean, you get this the following inequality, and then you're done. You change the object you want to use for your estimate, and you pick Fn to be so that. Okay, so now you compute, you do the same thing. So you compute chi of fn. Yeah, okay, this is, again, goes as q to the power 6. And this is greater than. And we know this guy to be positive. And then you go on. And then you proceed again with an estimate. From above. Which again is an estimate which goes as a qn to the power 4. And so you get a contradiction also in this case. So okay, I think I'm done. Also according to the schedule. Okay, thank you very much.
Continue the sequence of inequalities in higher dimensions. I mean, in some sense.
Yeah, so, well, we have a sort of a conjecture in for higher dimensions, but we still, I mean, still not completely sure that this would work, actually. So, of course, you need some kind of inequalities involving higher, I mean, CH4 and so on. Okay.
It's a question of guessing the constants, and maybe that's not so hard.
Yeah. So, I mean, it's you can guess. Of course, you get. So, of course, you need a quadratic inequality. So it's not difficult to write down one, but then to choose the one which works, it's not difficult. So it's very. I mean, already for other cases in dimension 3, it's
But in your generalized Bogomolov inequality, do you have some heuristic why the inequality has that shape? So you need something involving C3, but why is like C1 squared times C3 and not
So essentially, the heuristic, from my perspective, is that essentially, I mean, if you want to stick to the perspective that, as I was saying before, so you want to stick to the perspective that Emanuele used in the first lecture. So you want to construct stability conditions. Mm-hmm. So the point is that this inequality is the one providing stability conditions. So it's the estimate on CH3 you need to have a Z function which works, so that such that the image is contained in the upper half plane plus the negative line. So that's the issue. So of course, I mean, in other words, this conjecture is actually equivalent to another one. Involving only objects with nu equal to 0, so this stability equal to 0. Okay, and where you essentially have an estimate on CH3, a linear estimate on CH3. So CH3 is more or equal than 1 over 18 omega squared. Okay, and that's the inequality you need to prove that it's contained this way. So, and of course you can, as Emanuele was mentioning, you can vary a bit the parameters so that you can you can get this super property.
No questions?